So yeah, we're going to add on top of these light models a little bit, and while it's not important that everyone gets exactly what we're doing now, because we don't expect it necessarily to go into your projects, then you could want to do this because it's a cool effect. And also I just want to show that with what we've learned already, we can kind of add on top of this, and kind of more showing the power of what we learned and what we can add to this in a short amount of time. Once we've set up a nice light model, how nice it is to be able to add things on top of it. So I will start with a disclaimer that I actually haven't done this before, what I'm going to do now. I've used it, but in the fixed pipeline it was just part of the pipeline. So we're just going to kind of go through this together. So in that sense, we're going to start by kind of drawing a little bit up this vertex that we have here, or this imagined polygon that we're drawing, the vertex, which is part of the polygon that we're drawing right now. Let's go back into drawing here. The normal, we have a light, we have a direction to the light, we have the eye somewhere here, and we have a direction to the eye. And you can actually go ahead and just say, so this vector here was the vector v, this vector here was the vector s, this vector here is our normal. So this point here is our, we can call it point P, or we can call it just position, because that's what it's named in the shader. Okay, so we have the position of the light and the vector s, which we calculate from that. We have the normal. But we imagine that all of these things, this light here, is just omnidirectional, meaning that it doesn't matter if I'm drawing something that's here with this normal, or I'm drawing something that's here with this normal, this light will light all of those the same. The only thing that matters right now, if we just look at the diffuse part, is that this angle between where the vertex or the position is facing and this vector here, which is where the light is facing, or the direction to the light, that is the only thing that affects this. So it doesn't matter where the light is, it doesn't also matter how far it is away. So what we want to add is basically two things. Number one, can we somehow attenuate based on how far away the light is? And number two, if I add another thing and say the light itself has a direction as well. So we have a light direction here. And what I want to do, the effect I want, is that the light direction, basically an object that is here and is being drawn with this light, would get high intensity, but an object with its normal here facing this, but an object that's here, even if it has a normal that faces the light straight on, the Lambert would give high intensity because of the normals, but I want it to fade as it goes away from this center here, because this light is lighting in this direction. So I want something that is further away from this to be diminished, and in this direction as well. So here we get high intensity. As we go further away from being straight in front of this light direction, you get less intensity. So what would you want to do if we have these things? If we simply add to our shader a light direction, and we say this here is the light direction, and that's a variable that we now add to our shader, what calculations could we add here in order to get this effect that kind of diminishes?
With dot product of light direction and s.
Okay, the dot product of light direction and s, because s here is the direction between the light and the position. Actually, I think we'd need to use minus s in this case, because we're imagining s to be the direction from the position to the light. In this calculation, we're kind of looking at, because we want this angle, right? We don't want this angle. Other than that, it's the same. So, okay, yes. Exactly. So the vector S, if we take minus S, we have the direction from the light to the position, and then we have this direction from the light to wherever it's being lit at. So if those two are the same, or if those two are parallel, we'd get high intensity on that. Okay, so let's see if we can try that out. It's not going to be too difficult to put it into the shader, but it's going to be more difficult to actually kind of put it into our program so that we can view what's happening. But if we go into the shader here and add one thing, we have eye position, blah, 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 light position. Let's just add here light direction. Light direction. And so this needs to happen per light. So we're going to go ahead and say, well, light direction we can just use. So what we're going to do is at the end here, we're going to want to say, let's call it just spot attenuation equals, so that would be, we'll have the max 0 to make sure that it's in front, max of 0, and that would be the dot product of minus S and u underscore light direction, like so, divided by this dot product of this divided by, yeah, the length of both of them. Okay, the length of S times the length of u underscore light direction. Do we feel that this would be what we're looking for?
This around length calculations.
Length of S. Yeah.
Okay.
No, this starts here.
Already,
Yeah. To make sure that this is 1. This is the entire thing that's being divided with. Otherwise, we'd have divided first and then multiplied. Okay. So we have this spot attenuation now. But what do we need to do with that then? We probably have to say for this particular light and this particular part here, we'd have to say this is the effect that this light has on the color of this object, and we'd have to take the entire spot attenuation and multiply with that. Okay, so now we need to have some spot direction. Okay, cool. Let's go into the shader and say now we need yet another thing here. Or light position is here. Let's just set light direction in the same way. Okay, light direction location. Yeah, I need that variable then. We have light position location, light direction location. So set that in the same way here. U light direction, light direction location, and finally we need a function to set it. So light, set light direction. What am I doing wrong here? I already did that. Okay. So we have this, and now we just need to set it. So where are we setting the light position now? Let's just go ahead and say we'll set the light position to this fixed number here. We'll take this instead here and say, let's set the light direction. Okay, so light direction, we don't really need all of these multipliers here. We definitely don't need a y value because we want it to light straight to the side. And the cosine sign is just fine because the rest is just scalars, and since it's the direction, the scalars don't matter. And it's a vector, so let's put a 0 there. I think it won't matter in our calculations, but let's make sure. Alright, so now we've set the light direction. Okay, something isn't happy. Spot attenuation is an undeclared identifier. Did I forget to say vec4? Spot attenuation.
It's supposed to be float.
Yeah, true. It's supposed to be a single floating point value. Let's see if... Okay, let's take the light source itself now and stop moving that around. So let's just say light source should still be the position at the same place. Okay, let's look at the top-down image. I think that's a better place to look at this. Does it seem like it's doing it right? Yeah, it does, doesn't it? Cool. That was all it took. Okay, so now my next question is, let's say I find this spotlight to be weirdly wide. I want it to actually be a spotlight. This is like the diffuse calculation on the side of the sphere. It's like taking 180 degrees for it to go from full 1 down to 0. So if I want to add one floating point value that I can set in the shader that makes this more concentrated. Do you want to look at this while you think, or do you want to look at the nice graphic image here? So what we've got now is that we have this light direction here, and we have the direction to wherever we are, or wherever the position is, and we're taking this angle here. So if the light is directed to here, but the object is here, no, this is still giving us something fairly high. What if we want to diminish this, if we want to make it more concentrated? We've done this before in other calculations. In the specular calculations, we're doing the same thing. We're taking something that's taking 180 degrees to go from 1 down to 0, and we're making it more concentrated. What is that? Where are we doing this already?
Can't you just change the value of 0 where you're taking the max of to a higher value?
We could actually do that. Let's look at how that looks. That's not what I was looking for, but let's see what that does. Okay, so let's just say max 0.5. Let's look at it. Okay, yeah, max of 0.5, then then everything will actually be lit with at least 0.5. So we're thinking something else. We're thinking kind of a min. We're taking negative values and putting them up. No, we want to kind of... I get what you were thinking. You were thinking like, if it's lower than this, we want it just to become 0. So it's more like a clamp or something like that. Yeah, we could do that. We could put an if sentence and say if it's higher than this, then we just don't do anything, or something like that. But there's something else I'm looking for here. How do we do that? If we have something from 0 to 1 and we only want the... we wouldn't do a max of 0.5. We'd have to do a 0 unless it's higher than 0.5. Yeah. There's another thing we're already doing, and it's right here. It's in the screen right now.
The power function.
Yeah, okay. So what we're doing here, we have fung, which is a value just using a dot product, the same as the spot attenuation here. It's the same, it's just using other vectors. And we take shininess. The shininess is in fact an exponent on the Fung value to make it more concentrated. So if we just say, we want to go ahead and say, we have a spot direction here, light direction, and I'm going to go out on a limb here and change this to spot direction, and hope I don't forget to change it somewhere. Spot direction, I'm going to go ahead and say spot exponent, and say that's going to be a float. And we're going to go down here and say, so spot attenuation will be this. We said it was not light direction but spot direction. And again, we see we're taking the length of S here a couple of times and stuff. You can optimize this with that, but for now we're just doing all the calculations all the time. Okay, let's just do it in 2 steps and say spot attenuation equals spot attenuation to the power of spot exponent. Okay. U underscore spot exponent, yes. U underscore spot exponent, which is what we have here. I'm going to have to go into the shader and set a variable for that. So let's call it spot direction, spot exponent locations. We'll get errors here so we know where to change this. Spot attenuation, spot direction, no, spot exponent. Someone stop me when I'm spot exponent. Do I do this up here as well? No, spot exponent is there. And then let's go down and say, where do I have some function that just sets one thing? Set shininess, light direction. So set spot exponent, spot exponent location, spot direction location, and set spot direction. And we should get an error here, so we can go straight to here and fix this. Okay, so we're going to set spot direction to this. I'm going to go and say shader dot set spot exponent to say 10. Okay, let's look at it from above. You can see that there's a much smaller. I'm just going to take this camera as well and look at the whole thing from above. You can see that there's a much smaller cone kind of being lit at a time now. It's pretty weird though when it's in the vertex shader. We can see how the vertex shader is. No, this isn't working. This is so close here. It's so close that it's not affecting the closest ones because there are no vertices that actually fall within the cone. So that's weird again. We need to get this whole thing into the fragment shader eventually. So we have 10 minutes. Either we can get this whole thing into the fragment shader, or we can look at distance attenuation a little bit. So you can also see it here on the yellow one. It's just when it's, anyway, the spot exponent of 10 is maybe a bit high. We can add to this a spot cutoff and say you just set a spot cutoff angle to something like 45 degrees, and just say when the exponent has gotten it almost down to 0 anyway, we can just cut it off. And then we can just put an if sentence into our shader somewhere and say if this dot product here goes below something or above something, then we can just cut it off. So you can add a spot cutoff here, and that's not too hard, just an if sentence around the spot attenuation thing, and that way it's actually possible to use the spot cutoff for optimization as well, by doing the spot calculations before you do Lambert and Phong and diffuse color and all that, and say we do that first before we even calculate S and H, and if something is outside the spot cutoff, we can just skip the rest of the lighting calculations and just say that means that light 1 calculated color, that is the color for this particular light on this material, is 0, and just go on ahead to the next light. So that's a way to, the spot cutoff is a way to actually optimize a little bit as well. Okay, so anyone can do that if they want. Another thing we can do is to add a distance attenuation. And what we'd actually like to do in that case, if we, so here, let me just slide this out of the way. So the distance attenuation, the idea is basically that we'd want it to have the full value of 1 when it's like all the way up to, all the way next to it. So the formula that we set up for this is to say we're going to have 1 divided by something that we call constant attenuation, plus a distance that we have to calculate then, like the length of a vector between them, times a linear attenuation, plus if we want to add a quadratic attenuation, we can say the distance to the power of 2 times the quadratic attenuation. The idea here is that the default values of this would be 1 for constant attenuation and 0 and 0. And the default values here would simply give us 1 all the time. If we add a linear attenuation of 1, then we'll simply be dividing by the distance, so the further it goes away, the lower this will be, but it'll never really absolutely diminish. And if we add something to either the linear or quadratic attenuation, both of those will have the effect that the light will diminish pretty quickly, so we might actually want to take the constant attenuation up over 1. That is, put it to 2 or put it to 1.3 or whatever. Put it to a number that's higher than 1, because there aren't that many things that will actually be right next to the light. So we might want to compensate for the attenuation by kind of bringing the constant attenuation a little bit up. And this would simply be a factor here. We'd simply have to say, well, which vector would it be? That would give us the d. So d would simply equal the length of S. D here, this gets tiresome. So d here equals the length of S, and then we just put this into it, and we add values for the constant attenuation, the linear attenuation, and the quadratic attenuation. Do you want to do that and see what it looks like, or would you rather do something else? Would you rather try to take what we already have and put it into the fragment shader and see what that looks like? Okay, so for distance attenuation we have this formula here. We don't need to add all of these, but I'd say it's pretty important if we're going to add the linear attenuation that we add the constant attenuation as well. Or we can just stick that to 1. We can say we're going to add linear attenuation, and we'll just always say it's 1 divided by 1 plus the linear attenuation. And that way this will kind of diminish, and then you can just experiment with that. But let's go ahead into, okay, so now that we've changed the shader class this much, in order for us to be able to simply say change this to the fragment shader, we need to make sure that the shaders, so it's both a vertex shader and a fragment shader, but now we're doing vertex lighting. What we want to do is we want to take the shaders that are called fragment lighting, and we want to make sure that they have all the same variables as the ones we already have. So let's just open them up here, and we have to make the decision on which variables are we going to have to move, that is set to. So what we had here earlier was we were sending the normal as a varying, and the S and the H. So we were calculating, oh wait, fragment here. Can I move this to a, well, fair enough. So we have the fragment lighting, fragment shader here. I want to put it to the other side of the vertex shader. Okay, so we're calculating the normal, the S vector, the V vector, and the H vector beforehand. And we're taking the S vector, the normal, and the H vector, and we're saying those are simply going to be interpolated onto pixels and used in the fragment shader. So we did that already on Friday for a simpler light model. What we need to do now is we need to be able to take our new light model here. So let's just start by taking all of these variables, putting them into the vertex shader here to make sure we're not missing anything. Okay, so we have all of these, and the ones we're using here are really unchanged, so this doesn't matter. What we need to do now though is to go and say, in the vertex lighting here we were doing all of these calculations here, lighting for each light plus this, and then it's done. We're doing this in the vertex shader. Here we want to do that in the fragment shader. Somewhere in between here we need to stick this, and now we need to make sure that we have actual access to all the variables that we're using. So we don't need to calculate V and S and H because we're doing that in the vertex shader and then sending it through the interpolation. Are you following this? Just stop me if you want. Okay, we don't need, or we're already calculating Lambert and Fung, except now we're using these varying vectors here. Varying normal, varying S, varying H. So this is exactly the same thing. We're making this diffuse color here using this. We need to make sure that light color and material diffuse and all of these variables here, the color variables basically, shininess, emission, now those don't belong in the vertex shader, they belong in the fragment shader here. We're going to put them here. Okay, they're still part of the shader model, so we'll still be able to access them in the same way. I'm doing a lot of changes here, so the likeliness of this crashing and us not finding exactly where it happens are way too high. Okay, let's go through the Lambert, through the calculations here. So we have light color, we have that here. We have material diffuse, light color, material specular, material shininess. Okay, now the question is, with the spot attenuation, what would we want to send on through the varying, through the interpolation between the vertex shader and the pixel shader? So last time we sent the normals, we sent the vectors to interpolate. Is that something we can do now? Can we say, okay, the spot attenuation is going to be, just going to use this interpolated S vector here. We're using that already, so that's nice. What about the spot direction? Can we just trust that that's always the same? So Light is here. The S vector is changing depending on which vertex I'm using. But the spot direction, that's fixed, right? Yeah, okay, so we can just use that here. We don't even need to interpolate that. So use the spot direction. We have spot attenuation, use spot exponent, diffuse color, specular color, which you've calculated here. And for each light, then we have global ambient times material diffuse plus this and this and this. And we should now be able to simply stick that here, right? Just put that straight on the geofrag color. Okay, let's go through this here. We're calculating the normal and sending that as a varying into the interpolation. We're calculating the S vector, we're calculating the H vector. Those will be interpolated into the fragment shader. In the fragment shader, we're taking those in and we're using them like we used S and H and everything before. And now we just need to go in here and say we're now going to use the fragment lighting shaders. Nope. Okay, use spot direction, undeclared identifier. So we left spot direction and spot exponent in the vertex shader when they should have been declared in the fragment shader. Is that all? Nope. U global ambient, undeclared identifier. Did we do the same for that? Yeah, we forgot to take global ambient. Okay, so we can send data into these variables the same way. Once we compile these shaders together, it doesn't matter which shader has which variable name, we talk to it the same way. So we don't have to change anything in our shader class. But obviously, if I'm going to use something in the fragment shader, I better declare it in the fragment shader. But I don't have to change the shader itself. So now it should compile. Question is, does it crash? Okay. Do we still have this tiny exponent 10?
The normals, they are just interpolated from one vertex to another.
Yeah.
Then the spotlight, how can the spotlight? Okay.
So let's just draw this up a little bit. Time's up already, so class dismissed if you wanna go, but we can look at this for a while and just kind of figure this out. Again, we are in advanced stuff now, and I don't expect students to take this and put it into their projects just to get full marks. This is advanced stuff, and I'd be really impressed for a lot of this to be in a lot of the projects, just to make that clear. But we'd like to explore this a bit, and just to see that in the last, half hour or less, we managed to put this stuff in and make it work. But if we look at a drawing again, go here and kind of just draw what this looks like. Well, just the going from the fragment shader, if we're going to look at the light position and the light direction. Here. So we have a light position, we have a light direction as well. But the normal that we calculated here, we're not actually using the normal now, we're using the S vector. So we already calculated this vector here. And so basically, we don't have this geometry anymore. We just have this vector on one of the vertices. And when we calculate the vertex shader for another vertex, we have this direction here. So we have this direction. And then we have a fixed light direction or spot direction. So we can say that for the first pixel, this here will be the S vector, or the minus S. And we'll get a fairly high cosine here. Then for the next pixel, we'll have this one. Then for the next pixel after that, this one. The next pixel here. And obviously it's happening in 3 dimensions, so it's a simplified image here, imagining it's 2D. And it doesn't matter how many pixels are between these vertices, the interpolation will just be smaller. If there are more pixels, the interpolation for each pixel, the change between pixels will be smaller. But for the pixel in one vertex over to the pixel in the next vertex, it will be right here in the beginning and right here in the end. And for each pixel in between, OpenGL will simply say, okay, I have an interpolated vector. In this case, it's this vector somewhere on the center of this. And so this is a lower angle, smaller angle, which means we have a higher intensity on this. And even if we have two vertices here, we have S here, we have S here, we have the light direction here, and the light is so close that the spot cutoff simply makes it black on both of the vertices. We'll still get pixels in between where we get the light happening. There will be pixels in between where we'll have these vectors parallel, even though there is no vertex that actually ever calculates those vectors, because they're just linearly interpolated over the entire set. And that's what the fragment shader is all about. It's about taking whatever data you want to linearly interpolate per pixel, setting that up as a varying variable in the shader, and saying, I set this in the vertex shader, OpenGL will interpolate it per pixel for me. So you're not getting the same, the V normal here, and the V normal here in the vertex shader and the V normal here in the fragment shader, they aren't the same value, but we access them as the same name because they're linearly interpolated and we use them in the same way. So just sending these between and then doing the calculations per pixel, we get this. So we can look at again what this looks like here, especially here up close. You can see it even on the ones that are really close. We can see the circle of the spotlight. And if you look at it here when it's absolutely right next to it, you can see it as a small circle there, the spotlight. If we go back to the vertex lighting, go here, and it doesn't even affect the vertices, the polygons closest to it, because those polygons have vertices here and here and here, and none of these vertices are close enough to this circle that is supposed to be here ever to be lit. And that means that because we're only linearly interpolating the color, we just get a dark color here, a dark color here, a dark color here, and that dark color is then linearly interpolated over the entire thing, and we just get the same flat dark color. Whereas in the other case, we don't calculate the color here and here and here. We just calculate normals or vectors here, here, and here. And these vectors are linearly interpolated, which means that when we calculate for these particular pixels, we'll be using vectors that are a weighted average of a vector here, the vector here, and the vector here. And we'll actually get for these pixels linearly interpolated vectors that suddenly add up and line up nicely enough to actually give intensity on this really, really small cone. I'm going to take the spot exponent and make it a little bit smaller. It's kind of ridiculous as it is right now. And again, we have this kind of small circle, but it's a bit bigger. But still, it's having the same effect on this structure here as it is here, because we're not attenuating on distance. Questions?
For multiple lights in the shader, is it possible to have something like arrays in the shader?
Yes, it is possible. It is possible to have structs, like in C++, and you can have arrays of those structs. I don't have much experience in using that, and obviously when you're kind of using array operations and stuff inside code that you don't have that good kind of debugging possibilities on, it might be complicated. But yes, you can, but you're going to have to, well, you can just look at the shader language definition or find a shader language reference guide or something like that online and just find out how it's done. I have done it. The problem for me when I did it first was it worked on my computer, but I was trying to build a project that was supposed to be compiled for Android. When I put it on Android, the shader language that I was using there, the version of the shader language on my Android phone, didn't handle the complex operations that I was doing. So it basically took all the structs out and that stuff. But before I realized exactly what it was that my shader wasn't handling. So I'm not even sure if it was the structs, but I kind of disassembled that at that point. And besides, my phone or any phone that we tried it on didn't handle per pixel lighting anyway. So we simplified our light model a lot in order to make it work on the phone. So that's the only experience I have on using structs, but I did get them to work and they worked fine. And I could actually, the only thing with that, I don't remember exactly how it was, but so the locations here, you need to say, I'm going to get the location for some particular thing. And I think you can actually say, I'm going to get the location for something in a struct number something. But then you're not really getting that structure out. Or you have to send them in as basically arrays of numbers. So you have to look at your struct in your shader file. So if you build a struct here, struct light, and then inside your struct, inside your struct you put something like float, attenuation, and vec4 something. What you have to do when you send data into this is you have to basically look at it and see how many numbers do I have here. And you have to send an array of floating points of that size, and then they'll kind of line up to fill in this struct. So you might even have to kind of think of it as buffering 4 and 4 into each variable and think how the array you're sending in. At least when I did it, I had to do tricks like that. It wasn't hard, and I just Googled it, and some nice web page told me how it worked. But it was more than just being able to make a struct here, building it here, and then making the same struct in Java code and sending that over. You had to kind of formulate the data that you were sending in correctly so that it would fill the struct correctly. But another thing you could do, though, instead of actually making a struct of light and having an array of those structs inside your shader, you could instead say, okay, I'm going to have an array of light colors, and I'm going to have an array of spot directions, and I'm going to have an array of spot exponents. So each of them will just be indexed the same. So all of them on the index 0 will be for the same light. All of them on index 1 will be for the same light. But again, in order to fill this, you have to make sure you're sending the correct type of data in, and in the correct size of array or buffer when you send it in. But no, yes, you can do that, but you have to make sure that you're on top of everything. It's not complicated though, but I'm not going to specifically cover that here, because we can do everything that we need to do just with this. But yeah, I put a link to a quick reference of the shader language, or the shading language in there, so you can see all of the operations and all the stuff you can do there. Have we done enough now, or do we need something more? I'm going to make sure everything is let's see if it works now. Yeah. Okay, so here we have our fragment shader version of this. Alright, let's just finish building the attenuation for this light. So as we already looked at in here, the attenuation model we're going to set up is this. Well, let's just write it out here. We can say it's basically 1. We can just write it up in the code itself. So we're going to calculate the distance of a vector from the light to the position, and we already have that vector. It's the vector S. So let's go back here and say what we're going to need here. And you might as well do this in this fragment shader, but let's add it to the other shader as well later on, because we have all of this in the vertex lighting, vertex shader. We have the spot exponent. We have all of these calculations here as well. Okay, so what we're going to add is basically we're going to say, okay, we have spot exponent here, form float. So we're going to add a constant attenuation. We're going to add a linear attenuation. And we're going to add a quadratic attenuation. So let's just start by adding, or let's just start by adding it to the shader itself. So we're going to need, as before, let's keep this a little bit separate here. We're going to need 2 more of these. One of them is the, no, 3 more of these, constant attenuation. Quadratic attenuation and the linear attenuation. Okay, so we're going to need to grab handles for these as well. We have the spot direction, spot exponent there. So we need our attenuation here. This will be the quadratic attenuation location. So we have constant linear right, and as before we also need a way to actually set this. So we have spot direction here, spot exponent here, and we need to set single float, so let's just steal this one. Set constant attenuation. Okay, this should not be shiny here. Let's make it, not that it matters, but more readable that way. We already have the spot exponent there. So this is attenuation. So set constant attenuation. Again, linear. Linear and quadratic. So now we've gotten this out of the way. Now we have the mechanism to actually set this, and now I need to use it. So it's a simple enough addition here. So we have the spot attenuation now. Let's make another float, call it distance attenuation. This code can always be optimized a little bit by simply not making all these variables, but just adding on to the same variable all the time. But you can figure that out on your own. Float distance attenuation now be 1 divided by, now I need the distance. So I'm going to go ahead and just say float length of S equals length of S. Then I'm going to take this length and I'm going to stick it in here all over the place. So we're not constantly calculating the length of the same vector. Length of S. We could do the same for the normal as well, if we're using that in more than one place. Okay. Or we could actually take the length of S, then we could normalize S and just use S normalized here and not have to divide, but figure that out as well. So 1 divided by u underscore constant attenuation plus the length of S, which is our distance, d, times our linear attenuation plus the length of S squared. So we can either do pow of this and 2, or we can just do this times this. This squared times our quadratic attenuation. Let's just see if it compiles now. Okay, u quadratic attenuation undeclared. Quadratic attenuation. Here we have quadratic. Yeah, obviously. Quadratic attenuation, and I'm doing the same thing in the shader as well. No, I'm doing it correctly here. No, I did it up there as well. Okay, I'm hoping this is correct now, except maybe here. I hope this is correct. Now I look at it, I'm still not sure. Anyway, let's see if this compiles again. Okay, this compiles and works. I'm not yet really using these values, since we are not even doing anything with them here. They might even not be built. Okay, so we have a distance attenuation here as well. So now we simply add that to the whole thing. Distance attenuation. Now it would be a good idea somewhere here to put a little if statement in there, just to check that if the constant attenuation is 1 and the other two are 0, then we can skip calculating this and save a little bit of power. Let's actually set values to this to begin with. So we're setting spot exponent here, okay. Shader dot set constant attenuation to 1. Set linear attenuation and quadratic attenuation both to 0, and we should have an unchanged lighting model. Say yes, fine, okay. So this is what we're working with now. Here. Jump into the desktop launcher here. this. Okay. So nice. You can see on the yellow pyramid that it's being lit up exactly as much as the rest. So now I'm going to see if we can just jump in here and put linear attenuation to 1. That would mean that it would become 1/2 this formula here, this calculation here. You can see that as soon as length is 1 and linear attenuation is 1, then this whole thing is 1 plus 1, then we have 1/2. So it'll be halved it'll basically be halved at the distance 1. So this is a pretty steep attenuation. Let's see what this looks like. Okay, the yellow pyramid is not getting a lot of this attenuation. It's not really a linear function, even though the linear attenuation is linear, because it's linear, that is the part of it that's here. This part is linear to the length of s, but it's still part of the denominator here, so it's not going to be a linear function. But what we have here is it's really lighting this up fairly well. It's lighting this up much less. The sphere is being lit much. Yes, let's try different values for this now. Okay, we have this linear attenuation. What actually happens if we put the constant attenuation lower? Is we can see that the intensity really close kind of goes way high and actually kind of burns out. But that means this sphere here is getting a little bit more light. How low did we? And then have the linear attenuation a bit lower as well, so we can kind of use this to figure out exactly where we feel that this particular light is lighting the scene up. And obviously the linear attenuation, we need to set that kind of knowing the size, the relativeness, the size of the entire model we're using is the only thing that kind of, well, it needs to be relative as well to the size of the model, because we know if I were to take all the positions and translations and scales that I'm using now and just make them tenfold, that I could get the exact same image. The pyramids would look the same, I'd be going as fast, or I'd feel like I'm going as fast, but everything would just be scaled up relatively the same. Then we have to make sure that this distant attenuation is changed as well, because it's attenuating based on the actual distance in the global coordinates of the model. Okay, this is pretty nice. So here we have distance attenuation. And what I kind of want to do now is just to set the light differently and say, now I'm going to set the light position to the position of the camera. I'm going to see if I can find what I'm using. Cam.I.x cam.I.y and cam.I.z. So I'm going to set the position there. We have to actually set the direction as well, but let's look at how this looks like. Okay, it's spinning around. You can see it especially in this image here. But I'm kind of changing position. So I go here and then it's always being lit from me. but the direction is still changing regardless of how I'm turned. But the light position is following me around now. So I can see that it's more intense when I go closer, less intense when I'm further away. When I get really close, it gets kind of almost over intense. This is nice. Except now we want to set the light direction as well. To something, let's take this. Set spot direction. Let's see if we can do cam dot n. Okay, let's just go to dot. There's cam. So in camera, let's just make all of these public. You can also make getters and setters for them, but I'm just going to make sure I have full access to this. Let's go here where we have an error. Alright, cam.n.x. Actually, we're going to have to do minus that. Minus cam.n.y. Minus cam.n.z. So n is the vector that's turned straight backwards from our camera. And it doesn't matter whether I'm drawing from the point of view of the camera or the orthocam from atop, which is actually not an orthocam now, is it? I think we're actually setting it just to a really tight perspective projection. Well, let's stick to that for now. So what we're doing now is we're setting the position of the camera, position of the light, to the position of the camera, and we're setting the direction of the light to the negative n-axis. The n-axis, or the n vector, is the vector that's pointed straight backwards from the camera. So let's see if this works actually. Okay, let's see if this... Obviously when we go further away it gets darker, so let's go ahead again and see if we can set the constant attenuation to 1 again, just to look at the spot of this, and the linear attenuation to 0. Okay, so it's definitely following us around where we're looking. It's kind of more clear in this image here how the spot is actually, because the camera is also kind of narrow, so we don't really see outside of the cone of the light. So we could go ahead here and set the spot exponent really high again, so it becomes ridiculously narrow, and we can really see this. How this is an actual spotlight that's following us around, and we're using this spotlight to light ahead of us. I'm going to check the color of the light. Okay, it's a fully white light, it's just everything else is so dark. We could actually go ahead now and say we're going to set a little bit of specularity on something like this. Have it closer to white maybe. And this here. Something like this. Just see what happens here. So we have a little bit of specularity here as well. The specularity will always be a little bit weird because the light is also following us around, so it's always like straight on the center of the sphere where we're looking at it. And that's not the light source anymore, so we might as well take that out. Okay, so now we actually have a light following the camera around, and we have no distance attenuation at this point. Let's see what it looks like if we just change the quadratic attenuation. Huge. all until I'm right next to it. Very strong. This is a bit much, so let's set it lower. 0.1 quadratic. Let's see what that looks like alone. It's still having a pretty strong effect. You can see that the yellow here is really fading out when we get very close. So let's say as soon as we do something like 0.1 here as well, everything is going well. It still works. It feels a bit darker, but we still see it even that far away. It still has some effect. We just have to set this depending on what your model is like. Then we can make another light, put that on the light source there, and everything will be very nice. Okay, so right now I'm setting the spot direction to the camera, and I can set it back to here. I'm setting the position to here. I can set the position again, where it's just like that. So we have it fixed on the light source, but it's attenuating as well. You can see how strong it is right next to it. And we can go back to what we did earlier, which was basically set the spot direction to whatever. It doesn't matter if we set the spot exponent to 0, we should get an omni light again. Nope, not quite. Yeah, the negative numbers. So I'm simply going to go into my shader then and say if attenuation, no, spot exponent u underscore spot exponent equals 0, do one thing, otherwise we're going to do something else. Let's see. We can do something like float attenuation 0. Attenuation plus equals spot attenuation. This would we would do anything else. Let's keep the distance attenuation unchanged. We can do an if sentence like this, if statement like that as well. We just say if this doesn't equal 0, do this. We can always say attenuation plus equals this. No, we have to multiply it. So let's just say equals spot attenuation here. Can't do this either attenuation equals 1, obviously that's the base attenuation. Attenuation equals 1. Then we multiply that with the spot attenuation, if we're actually doing this. We multiply that with this, and finally we just say attenuation. And this, let's see what this looks like now. Okay, now we just have an omni-light. It lights every direction, and it's positioned there where the light is. So then we can go back here to setting the light position to something like this, and actually see that the light is now, oops, I have to make sure that we're actually translating the light source model there with it. This looks sort of right. Light source there, going around, the light is following it. It's an omni-light with no spot. So now I have no omni-light with no spot. I'll go back in here and say, as soon as we set up some spot direction, let's just make this, oh no, just some spot exponent here. Suddenly this light isn't lighting in all directions, it's lighting in the same direction. You can see that there on the pyramid, it's only lighting, and it never lights the sphere because it's never lighting inward. So if we were to just put minus here and minus here, now it would only light the sphere. And actually it also lights the side of the pyramid that's on the other side of the sphere when it's turned that direction. But we can see that it's always lighting into the circle that it's rolling around. But as soon as we take the spot exponent and set it to 0, we have an omni-light lighting all directions, so we can see the effect of it on the yellow pyramid now as well, except because of the distance attenuation, that effect is fairly small. So again, constant attenuation to 1, quadratic attenuation and linear to 0. We have an omni-light with no distance attenuation that just lights in all directions equally. So go ahead and experiment with this. Have fun. And it doesn't matter, I mean, it's the exact same lighting calculations that we have now here in the fragment shader as we could have in the other one in the vertex shader. So we take the attenuation part here, like so. See if we can just stick that in here instead of all this, like so. Go in here and take the new constant attenuation and that stuff, put it in somewhere out here. Let's see if we can go into the shader and just set the files that it's reading from to the vertex lighting shader pair. Does it crash? Yes, it does. v_s, of course. And there was more we need to do here. No problem though. Here we have to calculate length s. Go in here and find, we're calculating length s just at the top of the lighting. Right here. Okay, length s would still be the length of just a regular s. Now length s should work. But what we're also doing is we're using vs here. length S is calculated from the regular S. Length S, okay. It should work now. Except now again we see the artifacts because all of this is happening per vertex and not per pixel. So it all looks kind of different. We don't get the same detail, but we have the same control still. We can go ahead, can even take the sphere graphic and make it less detailed here. Let's try it. And we can go ahead in here and we can set the linear attenuation to something and the quadratic attenuation to something and set the spot exponent to 3 again. We can actually set the light position just to a fixed position again. I can probably see the same thing happening here. I need to set this to a fixed position as well. Okay, but what we see here is that when it's lighting straight on these polygons that are right next to it, it's not hitting the vertices in any way that builds up a high light intensity. So it's doing the same thing, it's still turning in these same circles, it's working, but it just doesn't have the same detail. But even with the polygon here, the sphere here with such a low polygon count, we can switch back to fragment lighting shaders and see that even then with this low poly count we're still getting this super detail on the lighting. So per pixel lighting is really having an effect. Same thing if we again put this in here, put it here, and go ahead and let's just skip this code for now. We actually can skip this as well, setting all the material for that. For the light source, and I'm going to go back to setting the spot direction to the camera and the spot position to the camera as well. Okay, so now we have this. Let's set the spot exponent higher. You can see it's working. We have this spot circle here, but as soon as we go close to something, its lighting falls out. And you can see that as soon as we go right next to a vertex at the corner of something, it gets really nicely lit up. Like so. As soon as we look somewhere else, we're not pointing the light at the vertex itself, nothing happens here. And the whole thing goes dark. It's working. Pointing it at a vertex, then it just goes dark when we're not pointing right at the vertex. Same thing here. If we switch again to the fragment lighting, we can go right next to the vertex and we get the light right on the center of it. Super nice. Alright, so that's more or less it for the lighting and the shading. If you have any questions, just feel free to send me an email or ask me in class to get better detailed explanations of all this. But you should pretty much have everything you need to build a really nice and complex lighting model. And all of these things, these last things here, we're looking at advanced stuff, so don't worry about it if it's not something you see how you could use in your program or how you should set up.